Hey everyone, and welcome. Today we're tackling a really interesting design problem, building a task manager. We'll need to create a system that can add, edit, remove, and, most importantly, execute tasks based on their priority. Let's break it down together. So here's the core challenge. We need to build a class that manages tasks. Each task has a unique task ID, a user ID it belongs to, and a priority value. We'll need to implement several functions to interact with these tasks. The problem asks us to implement 5 main operations. We need to initialize the manager with some starting tasks. Then we'll need methods to add, edit, and remove tasks. The most interesting one is the execTop function, which is where the real logic comes into play. Let's zoom in on that execTop rule because it's the heart of the problem. We're not just looking for any task. We need the one with the absolute highest priority across all users. But what if 2 tasks have the same top priority? The problem gives us a tiebreaker. We then choose the one with the bigger task, ID. After we find this task, we execute it, which means it gets removed from the system, and we return the ID of the user who owned it. Okay, let's trace the example to see how this works in practice. We start with 3 tasks. The one with task ID 102 has the highest priority of 20. Then we add a new task, but its priority is low, so task 102 is still on top. Now things get interesting. We edit task 102 and drop its priority way down to 8. Suddenly, it's not the most important anymore. The task with ID 103, with a priority of 15, is now the top task. So when we call execTop, the system correctly picks task 103, removes it, and returns its user ID, which is 3. To build this system efficiently, we need the right data structures. Think about the operations. For editing or removing, we're given a task ID and need to find that task's info fast. A hash map, or a dictionary in Python, is the classic solution for this kind of instant lookup. On the other hand, for execTop, we need to constantly know which task has the highest priority. This is exactly what a priority queue or a Max-Heap is built for. It always keeps the biggest item ready at the top. So our strategy is to combine these 2 powerful tools. We'll have a hash map to hold all the detailed information about our tasks, mapping each task ID to its user and priority. This is our source of truth. At the same time, we'll maintain a priority queue that only stores the priority and task ID, ordered in a way that lets us instantly grab the most important task. Here's the tricky part. Updating the map is easy. But how do we update the priority queue? Finding a specific task buried inside a heap and changing its priority is not something heaps are good at. It would be slow and complicated. So instead of trying to do that, we'll use a clever trick called lazy deletion. Here's how the lazy approach works. When we remove a task, we only delete it from our map. We leave the old, outdated entry sitting in the priority queue. We'll call it a stale entry. Similarly, when we edit a task's priority, we update the map, and then we just push a brand new entry into the priority queue with the updated priority. Again, the old entry is left behind. This seems messy, but we clean it up inside the execTop function. When we pop a task from the queue, we first check our map. Is this task still valid? Does its priority match what's in our official record, the map? If not, we know it's a stale entry, so we just ignore it and pop the next item until we find a valid one. Okay, let's look at the code. We'll start with our class, Task Manager. Inside the initializer, we create our 2 data structures, a dictionary called tasks and a list called PQ that we'll treat as a priority queue. Notice that when we get the initial list of tasks, we can just call our own add method for each one to populate our system correctly from the start. The add method is straightforward. We store the task's details in our map, and we push its information onto our priority queue. A quick note. Python's heap queue is a min heap, but we need a max heap. A common trick is to store the negatives of the numbers. That way, the smallest negative number corresponds to the largest positive number. We also negate the task ID to handle the tie-breaking rule correctly. The edit method uses our lazy strategy. We update the map with the new priority, and then simply push a new entry onto the heap. We don't even try to find the old one. For RMV, or remove, we just delete the task from the map. That's it. Super fast. The real logic is in execTop. We start a loop that continues as long as there are items in our priority queue. We pop the top item. Then comes the crucial check. Is this a valid task? We look it up in our map. If the task ID isn't in the map at all, it means it was removed, so we continue to the next loop iteration. If it is in the map, we check if its priority matches what we just popped. If they don't match, it means the task was edited, and this is an old, stale entry. We continue again. Only when a task passes both checks do we know it's the real, valid, top priority task. We then grab its user ID, delete it from the map, and return the user ID. If the loop finishes because the queue is empty, it means there were no valid tasks left, so we return -1. So how efficient is this design? Adding and editing are very fast, taking logarithmic time because of the heap push. Removing is constant time, which is fantastic. The execTop operation is also logarithmic on average. While in a worst-case scenario we might have to pop several stale entries, over many operations, the cost is spread out. For space, we need to store information for every task, so the space grows linearly with the number of tasks we manage. Let's recap the main ideas. The big takeaway here is that you can often solve complex design problems by combining simple, powerful data structures. We used a hash map for its super-fast lookups, and a priority queue for what it does best, keeping track of the most important item. The lazy deletion strategy was the critical glue that allowed them to work together, without needing complex and slow synchronization logic. It's a really useful pattern to remember for other problems. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. This channel doesn't make any money from sponsorships or ads yet, so if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.